When you merge onto a highway, that initial surge from 0 to 60 happens quickly, but as you approach your vehicle's top speed, that final crawl to the limit feels significantly more sluggish. Electric motors experience this exact same behavior when working against a mechanical load. Take a three-phase induction motor with a moment of inertia of 1 kilogram-meter squared. It's driving a fan where the load torque is proportional to the square of the speed. We need to calculate how many seconds it takes for this system to reach a target speed of 1,425 RPM. The math starts with the fundamental dynamic equation for motor drives. The acceleration torque is the difference between the torque the motor produces and the torque the load resists. That difference equals the inertia multiplied by the rate of change in speed. Using this relationship to find the time it takes to reach 1,425 RPM seems like a straightforward application of calculus. However, as the motor approaches that final speed, the relationship between torque and time changes in a way that often leads to an incorrect calculation. Before we can solve for time, we need to know the acceleration torque at every point in the process. That means we have to find the specific equation for our load torque. Since load torque is proportional to speed squared, we define TL as a constant, K, times N squared. If our rated condition is 42 Newton-meters at 1425 RPM, we can solve for K, giving us a multiplier of 2.068 times 10 to the negative fifth. Using this constant, we build a data table for our speed steps. Pause the video here and calculate the load torque, the resulting acceleration torque, and the inverse of that torque for the first 3 points, 0, 150, and 300 RPM. At 0 RPM, the load torque is 0. At 150, it reaches 0.46. By 300 RPM, it's 1.86. Subtracting these from the motor's output gives us our TACC values, which we then invert for the final column. With a fully populated table across the entire speed range, we now have the data points required to perform a standard numerical integration to find the total time. By rearranging our dynamic equation and converting our speed to RPM, we get the integral for time. We are essentially calculating the area under the curve of 1 over the acceleration torque with respect to speed. If we use the standard trapezoidal rule to integrate across our 150 RPM intervals, we calculate the average of the inverse torques for each section and sum them up. Following this method until we reach 1350 RPM gives us a total time of 4.33 seconds. But this result is an underestimation. Because of how we've approximated the data, 4.33 seconds is significantly less time than the motor actually requires to reach that speed. The discrepancy happens because of what occurs as the motor nears 1425 RPM. As the speed increases, the motor torque and the load torque begin to converge. This causes the acceleration torque, the difference between them, to become extremely small. When we graph 1 over that acceleration torque, the math reveals a problem. Because the acceleration torque is in the denominator, as it approaches 0, the value of the fraction spikes toward infinity. Look at our 150 RPM integration steps overlaid on this graph. The trapezoidal blocks are far too wide to capture that final spike. There is a massive amount of area, representing actual time, sitting in the gap between the blocks in the curve. When a dynamic system approaches its steady state, a wide numerical approximation will fail to capture the exponential increase in time required to bridge those final few RPMs. To get an accurate result, we must capture the area within that spike. This requires either using much smaller numerical steps or employing a graphical area method. There is one vital rule to remember. Never attempt to integrate to the exact steady-state speed. If the torques match perfectly, your acceleration torque becomes 0 and your time becomes infinite. In this case, we stop our calculation at 1400 RPM. We plot the curve on a grid where 1 centimeter on the x-axis represents 100 RPM and 1 centimeter on the y-axis represents 0.0003 inverse Newton meters. By counting the grid squares enclosed under the curve, we find an area of 155 squares. When we multiply those 155 squares by our axis scales and complete the conversion, the result is 4.87 seconds. This is the true acceleration time, accounting for the torque convergence that our previous table-based approach missed. To solve these problems accurately, keep 3 rules in mind. First, work from the base integral formula. Second, stop your integration at roughly 98% of rated speed. Third, use a fine scale to capture the nonlinear spike as you approach that limit.
Respecting the way these values diverge near steady state is the difference between a theoretical estimate and an accurate engineering design.